Okay, let's move on. Let's move on to the next presentation. We have Peter Hofstee, Dr. Peter Hofstee from IBM, who is also a part-time professor from TU Delft, is here, to talk about the OpenCAPI course. Another accelerator. I mean, it's a well-known accelerator. For the last several years, it has been there. So, Peter, please go ahead and start your presentation.
Okay, I hope you can hear me.
Yes, Peter.
Okay, and you can also see the slide, OpenCAPI course intro.
Yes, Peter.
All right, excellent. So what I'll do for the next half hour is I'll provide some general background on what motivated us to put this course together, and then I will give a brief overview of the course. As well as some links and so on. So these are the topics that I'll cover. I'll talk about memory-centric computing. I'll talk about some of the benefits and challenges of taking a memory-centric approach, and then I'll talk about how we address these challenges, and then I'll describe the course and provide an intro to that. So if we look at big data analytics, there's been, as everybody knows, there's been an enormous amount of growth in the amount of data that's available, right? In large part also because we collect a lot of data from sensors. At the same time, there's been an increasing desire to be very responsive with requests that relate to that data. So there's an increasing desire to have that data kind of at hand instead of tucked away in a storage system somewhere. So of course, computing from memory is nothing new. I mean, you could say that's kind of what computers do. But if you look at it at this scale, I think the history kind of is we've had in-memory key value stores for some time, things like Redis or Memcached. We've had in-memory databases, SAP HANA and DB2 are some examples of databases that maintain their tables in memory rather than on disk. And Spark, which is a big data framework, right, that kind of followed Hadoop, where Hadoop was really purely, I would say, storage focused. Spark is kind of a little bit more blended. It does have a somewhat standardized format for data in memory, but it's really, that data is usable within the Spark ecosystem itself alone. So what is new? What are we really talking about when we talk about doing big data analytics in memory? What is new here is that what we're going after is byte addressable memory, memory accessible with loads and stores, as you know them from the CPU cores, but the ability to share data in memory between applications, right? So quite often data in memory it's not possible to share it between applications because each runtime has a different way of storing data in memory, for example. So what we're talking about here is not just a file cache or a key value store, right? We're talking about random access memory that's OS managed, right, with through the page table and virtually addressable. So, this is a fairly big shift, right, with significant benefits and some significant challenges. The most significant benefit, of course, is that, unlike file systems that have been built on a notion of sequential access, memory provides random access. The other thing is that, when the data is in memory, and it's related to the first benefit, you avoid the deserialization cost, cost of getting data formatted in a way so it can be shared between applications. So today, quite often, right, when you go from one framework to another, even if you stay in practice within memory buffers, you have to go through serialization and deserialization to be able to, for example, follow pointers again in your target application that you want to communicate with. So we want to avoid that. Also, you know, in this model, there's no such thing as device memory that you may know from GPUs or for example, OpenCL type frameworks, right? Where quite often, in order to you know, access an accelerated device, you have to copy data to a particular memory space that the device can access. So here we're just sharing virtual addresses between all of the components, you know, different nodes within a cluster or accelerator devices attached to a particular node, and that allows for much more flexible accelerator integration. So what are some of the big challenges that this poses for us? Well, we need standard APIs and ABIs for you know, so to make sure that the data in memory can in fact be recognized across languages and frameworks. We also need hardware standards, right? So that we can, you know, physically attach nodes and devices that allow us to use memory sharing this way. And another challenge is that, of course, you know, memory isn't cheap, right? So holding more data is going to put even more pressure on memory cost, and memory cost is you know, quite often the most significant component of system cost to begin with. So, you know, putting even more pressure on that may look like you know, somewhat tenuous idea. And then finally, a challenge is that that if we do this, a lot of applications, and this of course is I guess I should have also listed it amongst the benefits, right, is that a lot of applications where the performance may have been limited by the performance of I/O devices such as disks and networks. If you hold the data in memory, then, you know, those limitations to a large extent are mitigated, and it's much more likely that your application is going to become compute limited. And we have already seen evidence of that in a number of different areas. So if we look at how we might address these challenges, so the first one, standardization of in-memory formats. So you know, I'll mention an example in the next slide. Apache Arrow is in fact, you know, is an Apache project that provides a good example of such a standardization for tabular data. Hardware standards, there are quite a few efforts. You know, of course, we on IBM and through the Open Power and OpenCAPI Foundation, we've been working on CAPI and OpenCAPI, and then there are also other standards like Gen Z and an upcoming one, CXL, that I'll mention. The next one is challenge is you know, to share memory more efficiently, or as a way to address the challenge of memory cost is by sharing memory more efficient. And I'll talk a bit about memory inception, which is a feature on Power 10 processors and something that we've already prototyped on Open Power systems with Power 9 and FPGAs in a project called Timesis Flow. And then finally, you know, having applications that are increasingly computation limited, of course, points you back at accelerators. So I'll talk a bit about making it easier to use and develop for accelerators, and that then also ties back to the course that I'll introduce. So first here, Apache Arrow. So you can see on the top right that Apache Arrow is indeed a very active Apache project with almost 50 commits per week over the last year or so, and it's already in its third year, I believe. So this continues to be a very active project. As I mentioned earlier, Apache Arrow standardizes the in-memory format for column-oriented tables. You know, they're actually fairly sophisticated because there can be nested structures and so on. The other aspect of these tables is that they're immutable, which means, you know, you basically write them once, and then the data remains the same, you know, until you destroy the entire table. And that is actually nice for some aspects of memory inception that I'll talk about later. It serves the need of being usable across a wide variety of languages and frameworks. On the language side, I think there's a dozen languages supported, ranging from C++ to Python, Java, Rust, and other languages. And also quite a few frameworks have support for this. You know, some have support to convert Arrow data into their internal formats and back. But other projects like Dremio or Fletcher provide, in the case of Dremio, a Spark-like framework that operates directly on Apache Arrow data, and in the case of Fletcher, an acceleration framework that operates directly on Apache Arrow data. And then there are also associated formats for when you do have to keep data in memory, on disk, or take it across the network. And these formats are called Parquet and Aeroflight, where Parquet is a compressed file format, and Aeroflight is a format for Apache Arrow tables optimized for communication over networks. The next way to address the next challenge that was to have hardware standards. So where Apache Arrow provides an example of a software standard, if you will, a standard for how data is laid out in memory. OpenCAPI's Gen Z and CXL provide standards for how to connect systems and accelerators to systems, and even memory within systems together. So this variety of new standards here, they provide shared virtual addressing as well as coherence. And Gen Z is targeted at distributed shared memory. And this interesting development that I heard of recently is that Gen Z is actually providing its specifications to the CXL project, right? So most likely switched Compute Express link is going to be a lot like what the Gen Z project was. You know, I'd say OpenCAPI is still a few years ahead of CXL. CXL is an industry-wide consortium. A number of companies, including IBM, are members. And actually, the functionality that CXL provides is, very similar to that of OpenCAPI. If you're familiar with OpenCAPI, you might know about the OpenCAPI memory interface, or OMI. Well, there's a standard CXL.mem that provides something very similar. The regular OpenCAPI standard to allow for shared memory acceleration is very similar to CXL.cache. And then CXL does also incorporate the old PCIe standard, but in a more packetized interface called CXL.io. The next one is about sharing memory, and I'll talk about and addressing memory cost. So I'll briefly mention memory inception. So with OpenCAPI, we can attach accelerators to a CPU and use virtual or effective addresses in the accelerator so that we can pass pointers from the accelerator to the CPU and back, right? And address memory through these pointers rather than having to copy data into device memory, for example. So what happens there is that a virtual address, actually in the case of power, it's an effective address because we have two-level address translation, but I'll just keep saying virtual. A virtual address through the page table gets translated to a real address. And then, depending on which port has that address range that contains the real address that address got mapped to behind it, if I do a load, it might actually hit memory on that particular port. So that means that really CPU is effectively a router. And if you heard the talk about Power 10 before, you might have heard that Power 10 has an aggregate bandwidth of something like 2 terabytes per second. So as a router, it's actually a pretty hefty one. So actually to use it as a type of router, the only thing you need to do is take that real address and kind of map it back to a virtual address that the next CPU can understand. So if you do that, then you can create a number of different configuration that address this memory cost issue. So one example here is I have a number of systems connected to each other through this memory inception interface. And now, if I have a workload that requires a lot more memory than a particular server has, like workload C in this case, running on this server, I can allocate memory on other servers, with the help of the operating systems and hypervisors that run on those servers, and incorporate it in the memory space in this server, right? So now instead of having to populate each of the servers with the maximum amount of memory that I might need, I only have to populate it with something like the average amount of memory that I need, and I can, I can amortize the cost of memory across servers, which is a big savings in memory cost. We can also create organizations where we have a very large server, like a 64 terabyte that the Power 10 supports as main memory, and kind of serve that out over memory inception to attached servers, which can then leverage that 64 terabyte space. Or we can even bolt more of these very big servers together and go all the way up to a 2 petabyte addressable memory. So, of course, this can be used with compute nodes, or accelerators, right? It doesn't really matter. And as I described earlier, this trick can be repeated, and you can use the servers as routers. So you can also get rid of your router infrastructure in a cluster of these servers connected through memory inception, which might provide a lower cost to create a high bandwidth solution. Of course, the more hops you take, the more latency you will add to your load and store instructions that hit memory in that place. So you have to be a bit careful here. But in principle, this kind of thing is certainly possible. And then there's actually a prototype of this. If you're interested, I would urge you to look at this project. It's on GitHub, all open source, where using FPGAs, we are able to realize this kind of an architecture on Power 9. And then about the final challenge that I was going to mention is that we're apt to become compute limited, right? When we have the storage and network challenges out of the way. So one framework that we built, actually the students from the group, now postdocs, many of them, in Delft did this, is a framework called Fletcher. So what it does is you provide a schema for particular data that is in an arrow table, and some information about how you would like to consume the data in these tables in an FPGA, and then Fletcher generates all the interfaces that you need within the FPGA, so you can only So you only have to develop the kernel inside the FPGA that processes that data. And you can use something like HLS, high-level synthesis, to build that kernel if you want to specify it in a language like C, C++. Or if you want, you can write that kernel yourself in a language like Verilog or VHDL. This makes it much easier to integrate accelerators like FPGAs within these big data frameworks, in particular those built around data held in Apache Arrow tables. So I'll spend the last few minutes here to talk about the accelerating big data analytics applications with FPGAs and OpenCAPI course, which very much follows the themes that I just laid out. It's about 7 modules. Each module is a handful of lectures. Each lecture is typically less than 20 minutes. So I think altogether, it's 20 plus lectures, I think. We first have a kind of a longer version of what I explained here, introducing the role of accelerators, talking about the importance of shared memory acceleration, doing a little bit more in-depth comparison of the different hardware standards that I mentioned here. Then an introduction into reconfigurable logic or field programmable gate arrays. OCXL is a framework that we use in OpenCAPI to also make the FPGAs attached through OpenCAPI accessible. And actually, when we use it with OpenCAPI, Fletcher is built on top of that OCXL framework. Then we talk about Apache Arrow and Fletcher. And finally, we have some application examples. So there's also some labs associated with this course that you can do. And there is I'm very happy that we bundled everything together into a VM that you can download and install that takes care of getting all the right versions of the tools and so on, so that you get a ready-made environment in which you can experiment with these with all of these frameworks and actually emulate FPGA designs. So I think that's trying to make it very easy for people to access this class, and it's free. So here are the links to the course material. The list of lectures they're all on YouTube. So there's the playlist, and there's a chat room associated with the lecture as well. And Fletcher, which I mentioned, is an open source project also. So there's ways to build on this further. I mean, if there are people here listening that want to create their own course, you're encouraged to do so. Also, if there are people that do projects and have new application-oriented lectures that they'd like to contribute to the course, we'd like to hear about that as well. And I guess with that, I'd like to leave a few minutes for questions. So I hope you can still hear me.
Thank you, Peter. Thank you, Peter, for the detailed presentation about the curriculum. I mean, the course which you and University of Oregon Professor Agiadas and Tu Delters, the people like Zaid and all these people, and also the PSI Philip, certainly put together a lot of effort to make it happen. And certainly I would like to see how many people can take up this kind of the OpenCAPI accelerator course worldwide. hoping that some of the people definitely will come forward and request it also. So, yep.
And I'll make the slides. I'll send them to you through Slack.
Yes. Yes. Thank you.
I assume there's a way for people to get them via you.
Yeah.
Any questions?
Yeah, I have a question.
Yeah.
The question is, did you have any kind of hands-on for students in OpenCAPI course?
Yeah, this is a very much a hands-on class, right? So there's a number of assignments that the team in Delft, in particular Joost Hausermans, worked on this, that he developed. Of course, these are self-graded in a way, right? Because we don't have a team to do grading, so there's no there's no official course credit that I know of. But we do provide also a short video to introduce the assignments, and I think a short solution video as well, right? So the idea is that students can download this VM, look, of course, go through the course material, look at the little video that introduces the problem, try to solve the problem themselves, and after they've worked on it, look at the solution video. So yes, it's very much intended to be hands-on and not just theoretical. And I guess I should have emphasized, right? So because we are using, we're using the FPGA synthesis tools and so on, but we're also using a simulator, right? So you don't actually need an FPGA to be able to take this class, right? We know that when we develop things and run it on the simulator, then later on, if we take it to a system that actually has the FPGA in it, things go very smoothly. If all you need is really just some laptop or computer that can run that virtual machine or container, and you're good to go.
Yeah, thank you, Peter.
You're welcome.
Thank you, Peter. Any other questions, audience? Oh, okay. There are two people raised hands. So let me open up one. Kiran Mehta first. Kiran, please go ahead.
Yeah. Can you hear me?
Yeah.
Yes.
Thank you, Dr. Hofstee, for the excellent presentation. My question pertains to in one of your slides you had shown that memory inception, and you could use memory that is quite far away also, and you had mentioned that one should be careful and mindful that the further you go, the more latency you're going to experience. So my question is that exposed to the user level applications programmer, and if so, then are there APIs to throttle that, or how is it done?
I see. Yeah. No. This is just load store accessible memory, right? So you don't, the load that you do doesn't depend on whether the memory is local or remote, right? Of course, if you share the memory between, if you modify it from different applications, then you do have to worry about coherence. In the case of, in the particular case of the Apache Arrow tables, actually that's fairly easy because they're immutable, right? They get written once and then they stay the same. But yeah, in general, no. It's just that if I do something like a pointer chase, right, and my local memory is like 100 nanoseconds if I do a pointer chase through the memory that happens to be attached to that particular node, I might get a pointer every 100 nanoseconds or so. If I go further and further away, right? Then
Mm.
if I do that same pointer chase, but I do it from one CPU to another one that is 5 hops away, you know, I might see an additional, in the order of 100 nanoseconds, you know, per hop, right? For other nodes. In the case of the FPGA prototype, I think we were, you know, we were under a microsecond, but that's with 2 FPGAs in the path, right? So it's considerably, you know, lower than that. When you would use a Power 10 processor that has that mapping back from real to virtual integrated in the hardware itself.
Yeah. Okay. Thank you.
My pleasure. Thank you, Kiran.
Thank you, Kiran Mehta. Thank you, Dr. Peter. Okay, I think in interest of timing, you know, thanks once again to Peter for the presentation during his, you know, the challenging time. Thank you very much, Peter. I really
pleasure.
appreciate it. Yeah, thank you.
Yeah. All right.
I hope everything
bye-bye.
is okay at your family side.
Yeah, doing all right. Thank you.
Sure. Thank you.
Yeah. Okay. Bye-bye.